Hello everyone, I am Ahmad Shaheen bin Abu Talib, a lecturer from the Department of Aeronautics, Automotive and Ocean Engineering at University of Technology Malaysia. So in this video, I will present to you my research title, Experimental Studies on Aerodynamic Performance Using Flow Control. So first we need to know the importance of aerodynamic performance, and to do the testing we need an aerodynamic model. And we need to know what is an aerodynamic model. So an aerodynamic model is the most important shape design part of an aerodynamic system, such as aircraft or UAV, for the airflow behavior so that we can test the acting forces on that aerodynamic model, such as the lift, drag, and pitching moment. And these models are widely used in applications to improve performance, enhance stability, and to increase overall efficiency. So besides aircraft and the UAV, there are other models that is critical for an aerodynamic performance, such as a cycling helmet, aircraft, UAV, a wind turbine, helicopter, sports car, and also wing ground, or WIG. So specifically on the cycling helmet, the most critical part of an aerodynamic performance is actually at the top part, where the surface needs to be smooth, and in an aircraft it's at the aileron or the wing part, and at the wind turbine it's at the blade, at the helicopter also at the blade, at the WIG is at the wing, at the UAV at the wing, and at the sports car it's at the roof and also the spoiler. So if we cut the cross section of a wing of an UAV, and then let's say we test it with an airflow, and the streamline across the airflow, you can see it's rather smooth. However, at a certain point downstream of the airflow, you can see a turbulent flow, and it will create a flow separation region. So the flow separation region is actually quite problematic for an aerodynamic performance. So what is actually a flow separation region? So the flow separation region is actually where the point of the flow starts to detach from the surface, and once it starts to detach, the turbulence occurs immediately. So if the flow separation occurs, the streamlines are disrupted, and it's quite difficult to maintain again an attached flow if the separation region occurs. And with this flow separation, it will actually decrease the lift. They will decrease the lift, increase the drag, and decrease the overall performance. And worst case, stall occurrence will happen that could lead to a disaster. So now the key objective to mitigate the flow separation is to maximize the lift, minimize the drag, and increase the aerodynamic performance. So what are the mitigation strategies? So first is the implementation of flow control. So flow control is a mechanism that is able to delay the flow separation and increase the performance. It works by enhancing the airflow, and the size of flow control is normally within the boundary layer height. So there are two types of flow controls. The first type is the passive flow control that require no external energy, and the shape and geometry are fixed on top of on the aerodynamic model. And the second is active flow control that require external energy such as air and electric power, and the control can be adjusted and also can be monitored. So some examples of a passive flow control are microvane, a motor ramp, and pump type that is attached on the aerodynamic model. So the advantages of the passive flow control, it doesn't require any control input or external power. It is quite easy to implement because you design it directly on the model. However, the disadvantages is that it lacks the ability to modify the output, and with the system attached on your model, this system is continuous towards the whole operational delivery. So active flow control type, they are normal blowing, and also tangential blowing, to name a few. So the advantage of it is that the control input can be adjusted whether you want a high power, low power, or medium power. It creates less parasitic drag because the flow control doesn't disrupt the airflow, and it improves the control maneuverability. However, it requires external energy. The power consumption for an active flow control is quite high, and the design for the active flow control is quite complex with the tube, the wiring, also anything else, which gives also heavier weight than the passive flow control. So in order to test the aerodynamic model with the flow controller in it, the first step of the experimental setup is having a wind tunnel with a test section. And there are also, with this wind tunnel, we can test several experimental setup, which is the particle image velocimetry, PIV. The second is the force balance system to obtain the lift drag. And the third is the oil dot visualization that gives the qualitative observance of the airflow. So for the oil dot visualization, in order to set up the oil dot, the environment needs to be dark. Before we put in the model inside the test section, there's a mixture of dot that is dotted in an array that has the same distance between each other. And then we put it in the wind tunnel, and as it reacts with the airflow of the wind tunnel, we can see several regions that can be seen on the model, which is laminar, transition, and turbulent. So the second experiment setup is the particle image velocimetry. If we test a flow control on top of inside the wind tunnel on the aerodynamic model, we can see that as the flow towards the model, we can see there's changes in vorticity downwards or downstream of the flow control, where this flow actually enhances the flow and gives an upwash and downwash momentum so that it delays the flow separation. And the third one is the force balance system, so that we can measure the lift and drag. So if we implement the flow control, we can see that the lift also increases in comparison with the baseline or no control or no flow control, and the drag coefficient for the flow control also decreases with only at a certain condition. So in conclusion, the flow control is a proven technique that can enhance aerodynamic performance. By delaying the boundary layer flow separation, it reduces drag and also increasing lift at a certain condition, and both passive and active methods have shown effectiveness in the real-world application. So that's it from me. Thank you very much.